student. My name is Mr. Najim Salih. I shall be taking you this course, Logic and Linear Algebra. So let's start with the first module, Module 1. Module 1 simply entails logic. What do we mean by logic? Logic is the act of analyzing language. It deals with learning the principles and methods employed in distinguishing valid arguments from those that are not valid. In this case, when we mentioned language, so we talk about statement. Statement simply means any declaration which may be either true or false, but not both. Any statement which may be either true or false, but not both. So we call such a statement. For example, if I say the number 2 is an even integer, it's a statement because it can be true or it can be false. Abuja is the capital city of Nigeria. It's also a statement because we can assign truth value to it, whether it is true or not. So those things are examples of what we call statement. Like for example, if I say, may God bless you. May God bless you in this case is not considered to be a statement because we can't assign truth value to it. We can't say it is true or not. Like questioning, if I am saying, when are you coming? It's a question. I can't call that a statement under this logic because we cannot assign truth value to it. We don't know whether, we can't say it is true or false. Like command, go out, get out. Those commands are not considered to be statements in this regard because we cannot assign truth value to them. So simply, statement is any declaration which is either true or false, but not both. Now, this leads to types of statements. Basically, there are 2 types of statements. We have simple statements and we have compound statements. Simple statement simply means a declaration which is either true or false, like I have explained previously. Like an example of simple statement. If I say, I am a man. I am a man is a statement. It can be true. It can be false. But it is simple. So that's an example of what? Of simple statement. The other one, compound statement. Compound statements is when we combine 2 or more simple statements together. So we have what we call compound statement. But how do we combine the 2 or more statements together? We use what we call connectives. Connectives, it can be and, which is conjunction. It can be or, which is what? Disjunction. It can be not, which is negation. It can be conditional statements, implies. It can be biconditional statement. But before you can have a compound statement, like I said earlier, there must be a connective. Like for example, I say, I am a man and I am a lecturer. I am a man, the first part, is a simple statement. I am a lecturer, also is a simple statement. But I use and to connect the 2 statements together. So that makes it to be a compound statement. I am a man and I am a lecturer. Now becomes a what? A compound statement. The next thing is what we call truth values. Truth values. This simply means the truthfulness or falsity of a statement. How true the statement is or how false the statement is. So we call it what? Truth value. Like for example, I say Canon is not in Nigeria. It's a statement because we can assign truth value to it, whether it is true or not. But the truthfulness of that statement is true. I mean, it's false because Canon is in Nigeria. But if I say Canon is not in Nigeria, it's a false statement. So now, the other one is truth value. I mean, truth table. On this truth table, when we get there, so we'll be using table to explain what we have been doing so far. So when I mentioned connectives the other time, connectives. Number one of connective is what? Conjunction. This conjunction, we use and to represent conjunction. And this is the symbol. This is the symbol of conjunction. When we are combining two statements together using and, so we call it what? Conjunction. The other one, we call it disjunction. This one, we use or. And this is the symbol for disjunction. The third one, we have negation. This one, we use not. And this is the symbol. It's if you are negating a statement. Number 4, we have conditional statement. Conditional statement. And this one, we use if. And this is the symbol, implies. We use implies for conditional statement. The fifth one, we call it by conditional statement. This one, we use if and only if. And this is the symbol. I mean, the symbol of it, by conditional. And this is what? By conditional statement. So we take this one after the other. Let me explain this conjunction. Like I said earlier, when we are combining two statements together using and, we call it conjunction. Like if I said, like I've said earlier, I am a man and I am a lecturer. So it falls under this conjunction because I use and to connect the two statements together. This one, disjunction. If I say, either I or him will come to your party. I use or to connect the two statements together. So we are under what? Disjunction. This one, negation. If I say, I am a man, how do I negate it? I am not a man. It's the negation of I am a man. Don't say I am a woman. No. If I say I am a man, to negate it will be what? I am not a woman. This conditional, we use if. Like if I say, I can only come to your party if I have money. That if me having money will imply my coming to your party. So it's a conditional statement. The last one, by conditional statement, if and only if. So now let's take an example of these connectives, one after the other. Number 1, we are dealing with what? Conjunction, which is what? And we use this symbol for the conjunction. This symbol. Let's assume we have two statements. Let P be one statement and let Q be another statement. So now we are having two statements in this regard, in this case. Now, how do I use table? Remember I mentioned truth table the other time. This is the table we are talking about. If I have P here, I have Q here. I want to find P and Q. And here, I have true, true, false, false. And here I have true, false, true, false. These two things are constant. They are like that. Anytime you are dealing with two statements. Now, how do I fill this place? You don't need to memorize anything in this case. You just try to understand what we mean by hand. Like for example, now if I say, hi and Tolu will come to your party. You know, I use and. If I and Tolu come to your party, it is a true statement. If I come, Tolu did not come, it's false. If I didn't go and Tolu goes, it's also false. So if the two of us did not attend, it's also false. Before I can have true here, the true statement must be true. Under this and, before I can have true here, the two statement must be true. This T stands for true, and this F stands for false. So now here, true and true, I have true. Two statements. If I have two statements here, I have false statement here, here becomes false. If I have false statement here, and I have true here, here become false. If I have false and false, this one now also become false. Before I can have true, the true statement must be true under the conjunction. Now, number 2, disjunction. Like I said, I have or, and this is the symbol for disjunction. For example, now I am still referring to this statement. We are adding two statements, P and Q, to be our statement. Now I have this P, Q. We are to find P or Q. Remember I told you this place is constant, true, true, and here is what? False, false. And this place, 1 true, 1 false, 1 true, 1 false. We are to find these two P or Q. How do we go? Before, in this case, at least one statement must be true before you have true here. At least one statement must be true, then you have a true statement. Like for example now, true or true. I have true. I said one, at least one must be true. True or false. Here becomes true. False or true. Here becomes true. And false or false. Here is what? False. Because before we can have true under this disjunction, at least one of these statements must be true. That is all about disjunction. The third one, number 3, negation. Like I said, negation, we are using what? Not. And this is the symbol. So this one, if a statement is true, to negate it, it becomes false. Like for example, if I have my P here, and here is what? Negation P. If my P is true, here becomes false. And if my P is false, and this place will become true. Simply just negate. When you have a true statement, it becomes false statement. When you have false statement, it becomes true statement. That is negation statement. The fourth one. Let me clean this side. The fourth one is conditional statement. Like I've listed before, conditional statement. This one, I said if. You know, if means condition. It's a conditional statement, if. And this is the symbol, implies. So implies. In similar way, we have P, Q. Remember, we are considering two statements right from the start. P and Q are our statements. We use P to stand for one statement, and we use Q to stand for the other statement. So now, we are to find P implies Q. Remember I told you, this place is what? True, true, false, false. And this place is what? True, false, true, false. How do we get this implies? True statement, if a true statement, can a true statement implies true statement? Yes. A statement that is true can also imply true statement. So it means T implied T here is what? True. Can a true statement imply false statement? No. The moment we call something true statement, it can never imply false statement. So T imply F, here we have false. A false statement can imply true. That one is yes. A false statement can imply true. So now here I have true T. False statement imply false statement. Yes. So yes means what? T. So now we have T, F, T, T. Where we have F is when we say true statement imply false, which is no. So true cannot imply false. So here we have false statement. So the rest are what? Are true statements. So this is what? Under conditional statement. The last one, but not the least, biconditional statement. We have done with conjunction. We have done with disjunction, negation, and this one, conditional statement. So the last one is what? Biconditional statement. So now I told you this one is what? If and only if. It goes front and comes back. This is the symbol. Biconditional. Let's take example as we did for the rest. We have P, our statement, and we have Q, our statement. We are to find P if and only if Q. Here we have true statement T, T, F, F. Remember I told you T stands for true statement and F stands for false statement. The next one we have true, false, true, false. These two statements are like that. So now we have to find P if and only if Q. Biconditional. Now, like we did here, under conditional, I said truth T implies T in the front, which is yes. But if I'm going back from this one, can T also imply T, which is yes. So now in this case, because we are having two arrows, it goes front and also comes back. T implies T, yes, in the front. T implies T, yes, in the back. So now the two are T. So it means here will be what? T. The second one, T implies false. This one is false already. Because I told you that true cannot imply false. So now T implies false is a false. Don't even do the second one since it is a false. So now here will be what? False. False implies true. Remember here, under conditional, false implies true is true. But this one is in the front. And since we are going front and we are also coming back, false implies true, true. But can true imply false? No. So now, since one has failed, so here becomes false as well. False implies false, yes. False implies false, yes. So here becomes true. So, like I've been saying, so we have done with the connectives: conjunction, disjunction, negation, conditional statement, and biconditional statement. So the next one now is derived truth tables. Every compound statement has a truth table that can be constructed from the truth tables of its component statements. This type of table is called derived truth table. For example, construct the truth table for the compound statement. Like this example now. It says, example 1, we are to construct a truth table. Construct a truth table for the compound statement. For the compound statement. What is the statement? We are given P and Q and negation P. This is what we call compound statements. So we are to construct table for this compound statement. The first thing to do, you check your statement very well. How many statements do you have? That is the first question you ask yourself. From this, we are having two statements, P and Q. We are having two statements, P and Q. This negation, this one is not a new statement. They negate P. So that's where we have negation of P. We can't call it a new statement. So now, logically, we are having two statements. So now, you say solution. You draw your table. Since you know we are having two statements, it means we have P and we have Q. This, our compound statement, will appear in the last column. But before we write this compound statement, you will now be writing the information you have from the question. You know, from this question, there's a place where we have minus P. So you give it a column, minus P. Since we can see it in the question. Another one, we can have P and Q. There's a place we have P and Q in the question. So now you give it a column, P and Q. What can you see again? We can see P and Q, this bracket, and this. So everything will now appear here. P and Q, and my negation of what? Of P. You know I told you this question will appear in the last column. So now let's fill. Like I told you earlier, that if you are dealing with two statements, this P and Q are constant. Like you have true here, you have T here, you have false here, you have false here. And this one here, you have what? True, you have false, you have true, you have false. Remember, I've explained the meaning of negation earlier. That when you have T, it becomes false. When you have false, it becomes T. So now, and since I'm dealing with P, nothing concerns me with Q. As you can see now, I am having negation of what? Of P. T here becomes what? False. T here also becomes false. False here becomes what? T. And false here also becomes T. Since we are dealing with what? Negation of P. This one, this column, you remember I have explained the rule under conjunction, and. Before you can have true statement, the two statements must be true under and. So now T and T, here I have T. T and false, here I have false. False and T, here I have false. False and false, here I have false. Since you have understood the rule under conjunction. The next one, this bracket and minus P. What is the bracket? T.
And you know the rule of and. Like I said, before you can have T under this and, the two must be true. So now, T and F, here is F. False and false, here is false. False and true, here is false. False and true, here is also false. So this one is what we call derived truth table of a compound statement. This example is like this. If you are having a compound statement like this, you first of all check how many statements do you have. In this case, we are having two statements, P and Q. So you now draw the table. You now check every information you have in your statement. I can see minus P, so that's why I give it a column. I can see P and Q, so that's why I give it also a column. And I can see the rest, so that's why I write it in the last column. So now I apply the rules of this, so that we get this one as our answer. The next one is logical equivalence. Logical equivalent, two compound statements are said to be equivalent if they have the same truth value for all logical possibilities. It is symbolized by this. This is the symbol of logical equivalence. Remember, this one is equals to. This one is equals to. But this one, you are having three of it. So we use it for logical equivalence. So now, for example, by the truth table, we should, by the truth table, show that the compound statement P, we are having this compound statement P or Q, and negation of minus P and minus Q. This minus simply means negation of Q. So we have to show that this statement and this statement are logically equivalent. This is the target. It means anything we get here must be what we get here. Otherwise, they are not logically equivalent. But if what we get here at the end and what we get here at the end of the table are the same, so we can now conclude that this statement and this statement are logically equivalent. So now let's do the table. Before you do your table, like I said earlier, you check how many statements do you have first. From this question, we are having just two statements, P and Q. I told you this minus P is not new statement. They negate this P. And this minus Q is also not new statement. They negate this Q. Logically, we are having two statements. So now we have P here and we have Q here. What can we see again from this statement? We can see minus P. Let me give it a column. We can also see minus Q. Let me give it a column. What can we say again? We can see P or Q. Let me give it a column. P or Q. What can we say again? This one and this. Minus P and minus Q. And what can we say again? This negation. Minus, negation of what? P and minus Q. I am using minus just to, the short form. So now we can see all this from this question. Well, remember, this place where I start and this place is what we want to check if they are the same. So if they are the same, it means they are logically equivalent. But if they are not the same, it is not. Now let's fill this place, these two places I told you. We have true T, false, false. And this place we have true, false, true, false. They are like that. And this one, we are negating this P, the line of P, the column of P, we are negating. Here we have T, this one becomes false. Here we have T, this one also becomes false. Remember negation, when you have true, it becomes false. Now we have false, here it becomes true. Here we have false, it becomes true. We have negated the what? The P, yes. Now go to the Q also. Here I have T. Since I'm now on the Q, T here will become false. False here becomes T. T here becomes false. False here becomes T. So now I'm done with this one. This one, this symbol I told you is or under disjunction. Or, and I told you under or that at least one statement must be true before you can have true here. One statement must be true before you can have true. So now let's see. True or true. Since we are dealing with P or Q. So now this is P and this is Q. True or true. Here I have true. True or false. Here I have true. At least one must be true. True. False or true. Here is also true. False or false. So here is what? False. Since it is at least one must be true under this junction. Oh. And the two here are what? Are false. So that's why I have false here. So we have done with this one. Now this one, you are considering minus P and minus Q. If you check, minus P and this and is conjunction. And you know the rule of conjunction. The two must be true before you can have true. So now let's see. False and false. The two are false. So here is what? False. False and true. Here is also false. True and false. Here is also false. Because I said true, the two must be true before you can have true. So now, true and true. Here is what? True. For this one. The last one, we are negating this one. As you can see now, this negation is at the back. It means we are negating this column. If you are having false, here becomes true. If you are having false, here becomes true. This one also becomes true. And this one becomes what? False. Now check where I start. This one and this one. Are they the same? True, 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 false, false. So they are the same. It means these statements and this statement are logically equivalent. By mere looking, they appear not the same. If you are looking at it, you say they are not the same. But if you use truth table, we get the same thing. So it means this statement and this statement are the same. They are logically equivalent. So that is what we are asked to check. So now your conclusion will now be, since this one and this one are the same, you now conclude that P or Q and minus P and minus Q are logically equivalent. That's your conclusion. So now this now leads us to tautology and contradiction. Tautology and contradiction. Tautology. A compound statement. I believe you don't have any issue with compound statement again. A compound statement is said to be a tautology if it has a truth value T, no matter the initial truth values of its component statement. What do you mean by this? Maybe you are given a question and you draw your table. The last column, if you are adding to T throughout, everything is true. So it means that statement is what? Is a tautology statement. Like for example now, and the other way around, contradiction. Contradiction, this one, when similarly a compound statement has truth value F. Remember the tautology is T, but for the contradiction is F. A compound statement that has a truth value F no matter the initial truth values of its component statement, is called a contradiction. The negation of a tautology is a contradiction. Like, I told you, for tautology, you'll be having true, 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 true at the end. And what is the negation of true? False, 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 false. So that's why we say the negation of a tautology, it simply means a contradiction. So for example, now let's take an example. Let's take an example for this contradiction, the tautology. Example 6. Use the truth table. Example. Use the truth table to show that P and Q implies P or Q. There's supposed to be a negation here. P and Q implies P or Q. Now let's assume we have this example. We are to show that whether this one implies this is a tautology or not is a tautology. So let's check whether it is tautology or not. How do you know? You use your table. Solution. Like I said earlier, anytime you are having a question like this, you check how many statements do you have. In this case again, we are having two statements, P and Q. And what can we see here? We can see P and Q. You can also see P or Q. We can also have negation of P or Q. And lastly, you can have everything. P and Q implies negation P or Q. This thing we are about to do, we are to check whether this statement is tautology or not. If this place gives us true, 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 true at the end, it means tautology. But if it gives us false, 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 it's a contradiction. Even if it is mixed, you cannot call it tautology. Before you can call it tautology, everything here must be true. So now let's check. T, false, false. True, false, true, false. This one, and, I believe you remember the rule of and. T and T, I have T. T and false, I have false. False and T, I have false. False and false, I have false. For the rule conjunction. This one, or T or Q, T or T, I have T. At least one must be true. True or false, I have true. False or true, I have true. False or false, I have false. Now let's check the negation of this. And assuming, okay. So please, let's remove this negation. As you can see from the question, there's no negation there. So let's remove this negation. It means this place will not be there. This place will not be there. Now let me rewrite this one. Since we are having P and Q, P, Q, this one is here, this one is also here. Now let's write this one. P and Q implies P or Q. So now let's check whether it is tautology or not. This one imply this one. True, T imply T. You remember the rule of imply, which is T. False imply true. True. False imply true. True. False imply false. True. I have explained the rule under this implication imply under conditional statements. I said true statement can imply true statement. Is yes. That's why I have true here. False statement can imply true. Yes. So I also have true here. False statement can imply true. I have true here. False statement can imply false. So I also have true here. Now, you can see now, everything here is what? True, 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 true. So since we are having true T here, it means this statement is what? A tautology. Since we are having the conclusion as what? T here, it means this statement up is a what? Tautology. The next one is what? Contradiction. Let me give an example under contradiction again as well. Like this example now. If this last column is false, 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 so it means we have contradiction. So now, example, show that P and Q and negation P or Q is a contradiction, is a contradiction. So we have to show that this statement and this statement are, it's a contradiction statement. So now how do we do it? We follow the same way as we did under tautology. Now you check solution. How many statements do you have as well? Like I said earlier, you are having two statements, P and Q. So now we have our P and we have our Q here. What can you see from this question? You can see P and Q. So now I give it a column, P and Q. What can we see again? We can see P or Q. P or Q. This one in the bracket. And what can we see again? We can see negation P or Q. And this one, you can see everything. P and Q and negation P or Q. So this one appears in the last column. So if everything here in the last column is F, 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 it means it's a contradiction. So now let's check. Let's fill this one. Like I said, true, true, false, false. This place, we have true, we have false, true, we have false. Remember the rule of and. T and T, we have T. T and false, we have false. False and T, we have false. False and false, we have false. Under conjunction. If you can see now, this one is what? Conjunction. P and Q. This one is what? Disjunction. Oh. So now T or T, we have T. At least one must be true. T or false, we have T. False or T, we have T. False or false, we have false. Under disjunction. This one, negation. We are negating this one. We are negating this one. P or Q in the bracket. So and the outside is what? Negation. So now this one becomes false. This one becomes false. This one also becomes false. And this F becomes true. Since it is negation. The last column, we are doing what? This place. We are considering this place and this place. Remember, we are using and in their middle. This place and this place. What is the middle? And. This and is what? Conjunction. So now let's check. True and false. Here is false. Remember the rule of and. The two must be T. The two must be T before you can have T. And since here I have one T, one F. So here becomes what? F. False and false. Here is also false. False and false. Here is also false. False and true. Here is also false. So what do we have at the end? Everything here is what? False, 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 false. So it means we are having what? A contradiction, statement. So now that is all about contradiction. The next one. So we are having laws of algebra of proposition. So we are having many laws. So this now leads us to what we call arguments. Argument. This argument in this case is the assertion that a statement called the conclusion follows from other statement called the premises. It is a set of statements that serves as premises together with another statement that serves as the conclusion, such that the conclusion supposedly follows from the premises. For example, now, if you're having an argument, those things you are bringing as your evidence, assuming to be premises, and the conclusion where you are going is conclusion. So that one is what? Conclusion. This argument is of 2 or 3 types. We are having valid arguments. An argument is said to be valid if its conclusion derives its support from its premises, and invalid if otherwise. So that is what? Valid argument. The next, a valid argument is always a tautology. If you are having a tautology using the truth table, that statement is a valid argument. That argument is a what? Is a valid argument. The next one is what? Sound argument. When the conclusion of an argument derives its support from the premises, and the premises together with the conclusion are true, then the argument is said to be what? Sound. All sound arguments are valid, but not all valid arguments are sound. So that is about argument. So we have explained the meaning of what? Arguments. So we are considering premises and we are considering conclusion. Like for example now, let's take an example. We are given, if they practice very well, they will win the match. Let me write the question. If they practice very well, if they practice very well, comma, they will win the match. They did not win the match. They did not win the match. Therefore, they did not practice very well. They did not practice very well. Now look at this argument. We call this one argument. If they practice very well, they will win the match. The second line says they did not win the match. And what is the conclusion? This therefore, anything after this therefore is a conclusion. It says what? They did not practice very well. So this is an argument. We are to use the truth table to check whether it is valid or not. The first thing to check from this question, how many statements do we have? That is the first question you ask yourself. Some may say 3, some may say 1, 2, 3. No. Some may say 4. 1, 2, 3, 4. No. You check very well. This if is a conditional statement under when we are previously when we were dealing with connectives. This if is what? A conditional statement. You not include it. They practice very well. It's one statement. They will win the match. It's another statement. So we are having two statements. This one, they did not win the match. They negate this one. This one, not new. This one is not. It's not a new statement. They negate. They will win the match. When you see now, they did not. This not is what? Negation of this. So this one is not a new statement. So that's why I said we are having only two statements. They practice very well. One statement. They will win the match. Another statement. This one, they did not win the match. It's like they negate this one. This one, they did not practice very well. They negate this one. I believe you understand how you can generate, you can get the number of statements you have. So now, since we have known that our statement, we are having two statements, so you can now let's say solution. Let P represent the first statement. They practice very well. They practice very well. That's our P. And let Q represent they will win the match. So now let Q represent what? They will win the match. So now we are having two statements. This one is a negation. They did not win the match. It's minus Q. Because Q is what? They will win the match. And here we are having what? They did not. It means minus Q is what? They did not win the match. You can see it is not a new statement. We negate this one. And this one, this therefore is a conclusion. Like I said earlier, they did not practice very well. Negation of what? Of P. Since P is what? Since our P is what? They practice very well. And here, they did not practice very well. It means minus P. They did not practice very well. These are the information we have from this. So now, how can we transform them? You now come to this word, if. Like I said, if is a conditional statement. How can I transform it? This first line, what do you see? If they practice very well, then they will win the match. It means if our P implies Q. Because you know that if is conditional, so it will imply. So now P implies Q from this first statement. This one, they did not win the match. You will now use and to connect them. And they did not win the match. What is symbol of that? Minus P. So here is what? Minus P. These two things now lead to what we call conclusion. So now you now bracket them like this. They will now imply the conclusion. So what is the conclusion? They did not practice very well. So what is the symbol here? They did not win the match. So here is what? Minus Q. And they did not practice very well. Here is minus P. This is the first. After you have interpreted your question, your argument, so this is the first thing. You can see now, from this argument, we get this compound statement. How do I get it? Let me explain again. This first line, this if is a conditional statement. They practice very well is our P. They will win the match is our Q. And this if is why we use implies. P implies Q. And if you are joining this one and this one together, You use and. And what is this one? They did not win the match. That is minus Q. If you check, they did not win the match, minus Q. So that's why I have minus Q here. So everything, these two things now leads to what we call conclusion. Therefore, so anything after therefore is our conclusion. They did not practice very well, which is what? These two things now produces this minus P. So now, after this one, we will now draw a table to check whether this argument is valid or not. But first of all, you interpret your question like this, you now go back to the table. I believe you have understood how we interpret the question. So now I am having this one. P implies Q and minus Q. Everything now produces our conclusion to be what? Minus P. Now from this question, we are having two statements, as you can see. Let's draw the table. We are having P and we are having Q. Two statements. What can you see again from this statement? You can see minus P. So let's give it a color. You can also see minus Q. Let's give it a color. We can see P implies Q. We can also see P implies Q and minus Q. Then lastly, we can see everything. P implies Q and minus Q. Then everything implies minus P. I believe you can see what I wrote. Minus P. That's our conclusion. So now let's fill this table. True, true, false, false. True, false, true, false. Negation. I have false, false, true, true. This one, negation of this. I have false, true, false, true. So it implies. I believe you remember the rule of implication. So now true imply true. I have true. True imply false. I have false. False imply true. I have true. False imply false. I have true. This one, and this. This one and this. So now, true T and F, I have false. False and true, I have false. True and false, I have false. True and true, I have true. The last one, this one implies minus P. You can see now, this one is minus P. So now, this implies minus P. False imply false, we have true. False imply false, we have true. False imply true, we have true. And true imply true, we have true. Now, this one is a tautology statement. We are having true, 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 true. Since we are having the tautology here, it means this argument is valid. It means we are having a valid argument. Since everything here is T, 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 the argument is valid. If they practice very well, they will win the match. They did not practice, they did not win the match, therefore they did not practice very well. Since we are having T, T, T here, it means that argument is what? Is valid. Now, let's move to the next one. We call it quantifiers. Sorry, quantifiers. A quantifier is a word that tells us how many. A word that tells us how many. It is used to quantify a statement. There are two types of quantifiers. There are universal quantifiers and existential quantifiers. When we say universal quantifier, this is a quantifier that takes into consideration all possibilities. Quantifier, all universal, all possibilities. It makes use of words like all, every. So that is the words. What we mean by universal quantifier. So it has a symbol. This is the symbol. So we have universal quantifier and we have existential quantifier. This one leads to what? To universal. Universal, and this one is what? Existential quantifier. Universal, we are using the word all, every. That is all, every, all, universal. This one we are using for some, or there exist. It is not all again. This one, this is the symbol. This symbol means what? For all other universal quantifier. And this one means what? There exist under existential quantifier. So this symbol, we'll be using this symbol for universal and this symbol for what? For existential quantifier. Before we take example, there's what we call a variable. A variable is an arbitrary symbol used to express a proposition or statement. It could be free or bounded. A free variable is a variable which is not predictable, which is not predicated by a quantifier. So now let's take an example of what we have been saying about quantifier. Remember I told you quantifier is of two types. We are having universal and we are having existential quantifier. So now let's take an example. And this one is used for universal, for all. And this one is used for existential, they exist. So now let's take an example under each of them. Example. Let a set A equals to 1, 2, 3, 4, 5. Determine the truth value. Determine the truth value. Determine the truth value of the following statement. Let's say of the following statement. I believe you remember the meaning of statement and you remember the meaning of truth value. The truthfulness or falsity of a statement. I've explained this one earlier. Truth value means what? The truthfulness or falsity of a statement. So now this example, number A, the A says what? This set, there exists X in A such that X plus 3 equals to 10. Number B says what? There exists X in A such that X plus 3 less than 5. Now these two things are statements. They are statements. As you can see now, they are statements. This one reads, there exists X element of A. You remember we have given A. It means our X can be 1, it can be 2, it can be 3, it can be 4, it can be 5. The value of our X. Because we are taking our X from this A. There exists X element of A such that X plus 3 is equal to 10. It's a statement, but they wrote it in code. And And this one again, there exists x element of A such that x plus 3 less than 5. These examples, we want to know whether these statements are true or false. That's why we are told determine the truth value of the following statement. Solution. This first one, number A. Remember we are having there exist. They use there exist. There exists x element of A such that x plus 3 equals to 10. What is our condition? Our condition here, x plus 3 equals to 10. And we are taking our x from where? From A. It means our x is taken from A. It can be 1, it can be 2, it can be 3. This statement is saying that one number exists here, that if I had it with 3, I will get 10. Is it true or false? So now let's check. I have 1. 1 plus 3. Can I have 10? No. Because 1 plus 3 equals to 4. Let's take 2. 2 plus 3. Can I have 10? No. 2 plus 3 equals to 5. Let's take 3. 3 plus 3 equals to 6. Can it equals to 10? No. We can't have 10. And from this statement it says that there exists a number here that if I had it with 3, I will get 10. So now we are checking. Let's check 4. 4 plus 3. Can it give us 10? No. The last one, 5. 5 plus 3. Can we get 10? No. We check every number here in our set. None of them gives us 10. And this statement says there exists. It means no one number exists that will give us 10 when we had with 3. So how do we conclude now? Our statement. It's a false statement. This statement is not true. It's a false. Because none of this number gives us 10. So your conclusion is what? This statement is a false statement. Assuming we have one number that when we had, suppose now there are 7 here. Assuming there are 7 here. If 7 is here, if I had 7 with 3, I'll get 10. So suppose 7 is here, so it now make this one to be true statement. But since there's no 7, we stop at what? At 5. So there's no number here that can be added to 3 and give us 10. Therefore, this statement is a false statement. The example number 2. So let me clean this conclusion. Example number 2, number B. It says there exists x in A such that x plus 3 less than 5. Like I told you earlier, we are taking our x from this set. It can be 1, it can be 2, it can be 3. And this there exists. Just make sure you get 1, at least 1 for there exists. At least 1. Like if I say, all of you will pass except 1. That exception, it has make it not to be all again. So now, this one, our condition here is what? X plus 3 less than 5. And we are taking our x to be from A. It can be 1, it can be 2, it can be 3. So now let's take 1 by 1. 1 plus 3 equals to 4. And we know 4 is less than 5. So this one is okay. Because we have seen 1. When we had 1 to 3 equals to 4. And 4 is less than 5. And so it means this one satisfied. This condition satisfied. No need to check for 2. No need to check for 3, 4, and 5 again. Since you have gotten 1. Because this statement, this one means what? There exists. At least 1. At least 1 must satisfy. So since we have gotten 1, no need to check for the remaining numbers. So now this statement, what is your conclusion? We conclude this one is a what? It is a true statement. At least we have gotten 1 to be true. Therefore, the statement is a true statement. Let's take take one more example. So the next example, determine example 2. Determine the truth value. Determine the truth value of each of the following statements. Of each of the following statements. If our A 1 up to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is our set. Number 1, number A says what? For all. Remember this symbol is what? For all. For all x in A, you can call it for all x in A, or for all x element of A. It means we are taking our x from this set, such that x squared equals to x. That's number 1. So now let's solve this one first. For all, remember this one is not there exist. There exists, I told you, at least one. So now let's have B. 2 of them. This one, for all x element of A, shows that x minus 4 less than x. Now, let's do these 2 examples together. This one is for all. The first example we did, we used the exist. And I believe you have understood how we simplify that one. So this one, we are using for all. Solution. The first one, number A, it says for all x in A, such that x squared equals to x. When you first see this thing, you may not know it is a statement. So that's why we said it is a statement in code. So they code it. How do you read it? For all x element of A, such that x squared equals to x. So now, our condition here is what? X squared equals to x. And our x can be 1 up to 10. Now let's check one by one. When x equals to 1, 1 square, can it give us 1? Yes. This my mark means what? Yes. Because 1 square is 1. X square is x. This one satisfied. Let's check 2. We can't conclude yet, since we are dealing with all. You can't conclude now, since we are dealing with what? For all. So now let's check. It must be true for every number here before you can have a true statement. But it has been satisfied with this one. Let's check 2. Can 2 square give us 2? No. Because 2 square equals to 4. This one failed. Don't check the remaining, since one has failed. Because before we can have a true statement, all must satisfied. The first one satisfied, but the second one failed. Since one has failed, don't do the remaining one. So what is your conclusion? This statement is a false. It's a false statement. Because one has failed already. 2 square can never give us 2. This 1 square give us 1. That one is satisfied. But 2 square can never give us 2. So this one failed. Since this one has failed, don't check for the remaining one. Because we are dealing with for all. All must satisfied before we have a true statement. So what is your conclusion? It is a false statement. Assuming this one is there exist, so it's a true statement. If this one is there exist, it's a true statement. But since this one is for all, so it is not a true statement. It's a false statement. The number B, let me clean this one. Let me clean this one so that we solve the number B together. For this number B, for the B, solution for the B. What is the question? For all x in A, such that x minus 4 less than x. Our condition here is x minus 4 less than x. And our x is taken from this set. It can be 1, like I said, up to 10. So now let's check one by one. And we are using for all. Remember, we are using for all. So now 1 minus 4 is minus 3. Minus 3 less than 1, yes. This arrow means what? Yes. Because if you say 1 my x, I am taking my x to be 1 now. 1 minus 4 is minus 3. Minus 3 is less than 1, yes. The other one, 2. 2 minus 4 is minus 2. Minus 2 is also less than 2, yes. Check number 3. 3 minus 4. This one is minus 1. Minus 1 is also less than 3, yes. The next one, 4. 4 minus 4 is 0. Is 0 less than 4? Yes. Let's check 5. 5 minus 4 equals to 1. Is 1 less than 5? Yes. I can't conclude yes because I must do for all. Since we are dealing for all. What is the next number? 6. 6 minus 4 equals to 2. Is 2 less than 6? Yes. The next number, 7. 7 minus 4 equals to 3. Is 3 less than 7? Yes. The next number, 8. 8 minus 4 equals to 4. Is 4 less than 8? Yes. The next number, 9 minus 4 equals to 5. Is 5 less than 9? Yes. The last number from our set is 10. 10 minus 4, 6. Is 6 less than 10? Yes. You can see now, every number satisfied. Since since all the numbers satisfied, so we conclude this statement is a true statement. So now, our conclusion, it is a true statement. So that is all about quantifier. So now the next one, application of quantifier. So now you can just check some exercises and solve. Because for every module, there are some questions. So for you at least, for practice. So when you check some exercises, so you will see, you will apply each one. One of the rows we have been saying. So this ends the first module. Thank you very much.